Hey, how's it going out there? Hello, hello. Are you guys having a good Wednesday? I'm having a sleepy Wednesday. Hey, what's up, Miracle? Hey, I'm glad you're doing good. So as you guys know, we have a test coming up on Saturday. And we're going to post it at 10 a.m. on Saturday. And then it's due on Sunday at noon. And we're putting the finishing touches on the test today. I was looking at it this morning. You'll have plenty of time to do it. I think it has some challenging parts. It has some straightforward parts. But you can do it. You can certainly do it. Friday, we're going to do a test review. It's going to be on Zoom. So we won't be here on Friday. Dr. Ligor and I are going to tag team a test review. Is this open note, by the way? Yes, sir. So it's open notes. Any course materials are permitted. So any of the textbooks that we list in the syllabus, and so like there's the Nelson textbook, which we put a couple chapters on UB Learns. There's two other textbooks that we list, and those are available online through the UB library. So you have those books that you can go to as well. But I think primarily the course notes are going to be your like go-to thing. You can use MATLAB, even though it's not required. But if you're like, oh, I want to do this problem in MATLAB, you can do that. You just gotta attach your code. So that's the thing. Yeah. It's all open notes. The only thing is there's no collaboration. So it's something you should do on your own. You shouldn't be talking to your friends. And that's okay. Dr. Lagore and I, you can ask us questions via email. And we'll have so I'm going to put all this information up, but there's going to be 2 time windows when we'll be you'll know that we're available on email. Okay, the course notes have been very helpful for the homework assignments. Are the questions similar to those? Yeah, the questions on the test I think are similar to questions you've encountered in the homework. There's some of them they have a little twist, just a little twist on it. Because it's a take home and it's open note, we made the problems have a little challenging edge to them. But it's all the stuff that we've been doing. It will look very similar to the homework. Same kind of notation and stuff. And like I said, we're going to even review on Friday to try to give you a better idea. So you guys be thinking, if you have some questions or concerns about the upcoming exam, ask us about it on Friday. I know tests can be stressful. That's just the way it goes, But try not to stress. Is the twist going to be blatant, or do we really need to watch our step? I think it'll be obvious. I think it'll be obvious to you. As you go through it, you'll be wait, this is just a little bit different, or something like that. And when I say twist, I don't mean we're pulling the rug out from under you. I'm just saying it's not going to be exactly an example from the notes. That's what I'm saying. But yeah, I definitely expect that. No. I don't want to stress you out, but I want you to. I would say that the test, it's not just a walk in the park. You're gonna have to put some thought into it, and I think that's good to know in advance. That it is challenging, and. And that's okay too. Don't let that stress you out, because we know what we're giving you. We expect it to be challenging, so but doable. Don't freak out. Okay, today I have a feeling this will be a slightly shorter lecture. That's the feeling I have. Let me tell you what we're talking about. Let's go up here. So this is building on what we did on Monday. So let me tell you what we were looking at on Monday. Or even let's roll it back even a little further than Monday for right now. What have we been doing recently in this class? We derived a set of equations that describe the dynamics of an aircraft. Okay, and the set of equations I'm talking about, these are the translational dynamics. So these have the forces. So there's 3 of those equations. There's 3 rotational dynamics equations. So those are the moments acting on the aircraft. Then there's 3 translational kinematic equations. And then there's 3 rotational kinematic equations. So if you add all of those up, those give you 12 equations that describe the motion of an aircraft. And these are nonlinear differential equations. What we're going to do is we're going to linearize these equations about some standard reference flight conditions. Now, when you do this, the equations get simpler. So an example of this is what we started looking at on Monday, which is called the longitudinal flight equations. Now, longitudinal, that kind of means along the nose of the aircraft. It's just giving you an idea of, this is forward motion of an aircraft, like longitudinal flight dynamics. So what I did last time is I set up what this reference flight condition is. And so let's spell it out. So this is this reference flight condition. This is the one we're using. The one I'm describing here is for longitudinal flight. And so let me break it down for you. We talked about this a little bit last time, but it's steady, meaning that u dot, v dot, you're flying at a constant velocity, and you're not, basically think of it that way. We're going to say that we're going at a constant altitude. That's what we call level flight. And that's different from wings level, but that's another condition we have. Wings level means that your wings are parallel to a flat Earth. I'm not saying the Earth is flat, but you know what I mean. Your wings are like level with the horizon. Okay, longitudinal flight is also non-turning. You're just kind of going straight. And coordinated, that means that all of your relative wind is coming from the front. You don't have any wind coming from the side. So if you can kind of visualize this, it's just an aircraft going straight, coming right at you. It's not turning. And so we've talked about reference flight conditions. It's basically you specify these conditions, and then variables in your equations that I described earlier, those get simplified or they get set equal to 0, and terms start to like drop out of these equations. And if you propagate these conditions through like the dynamics equations and so on and so forth, you come up with like a bunch of extra conditions. Some of these might seem obvious, and some of them you have to do a little digging to find out what they are. Like this one's a more obvious one. So this is little v is equal to 0. What's little v? That's the side velocity. So if I'm just going straight in an aircraft, it makes sense that I don't have any velocity to the side. I mean, if I don't have any relative wind coming from the side, okay, that happens. If my altitude is constant, then h dot, the time derivative of my height, that's equal to 0 because I'm at constant altitude, h is not changing, and so on and so forth. So a bunch of conditions fall out, and we've played with some of these before, and these show up in your most recent homework. So, you know, typically, like we said, I told you there's 12 states, there's 4 inputs, but for longitudinal flight, the reference condition that I just described, when you linearize the equations about that flight condition, we limit our scope to these variables. So instead of 12 states, we went down to 4 states. Instead of 4 inputs, we went down to 2 inputs. And on Monday, I was saying, I'm not sure why we can do this. So we tried to examine how are you justified in limiting the scope of our dynamics for this reference flight condition. And now I have a pretty good answer that I want to walk you through today. I have a pretty good answer. Let me tell you our strategy for today to explain why we can go from 12 states to 4 states. What we're going to do is we're going to derive the perturbation dynamics, which means the linearized dynamics, for each of the 4 longitudinal states. So you'll see what I mean as we go. But I'm going to give this right up front. Here's the spoiler. So we will derive, so these are the perturbation dynamics for U, W, Q, and theta. So these are just the 4 states that they say, these are all we need. So we're going to derive those perturbation dynamics. So here's the spoiler. Once you derive those, we find these equations are interdependent, or they're coupled, which means like U, if I change U, which is my speed, my longitudinal speed, that'll affect these other parameters. Or if I pitch up the nose of my aircraft, it'll affect the dynamics of those things, and vice versa. So you're going to find when we do this that all of these equations are interconnected. Hey, good afternoon, Rue. Long time no see, my friend. Okay, so you're going to find that these are interdependent. But here's the special thing. We also find these are not dependent on the other 8 states that we ignored. So that's the cool result. You find that for this flight condition, you have like this subset of states that depend on one another. And the other 8 states for this flight condition, they don't affect this. So when we analyze this flight condition, we just look at these ones. And it makes sense, like when you're flying just straight, it would mostly depend on these quantities anyways. Like U is like longitudinal speed, that makes sense. W is your speed component that's pointing along the downward direction of your body frame. So basically, these 2 variables together, that's just describing your speed. And you might pitch up or down a little bit. This is your theta's your pitch angle. And Q is effectively like a pitch rate. So basically, you're going forward, and you might change the pitch angle of the nose of the aircraft, and those are basically the only variables we have to pay attention to when you're flying straight at level altitude. So, okay. So that's the spoiler. We're going to find that they only depend on each other. So this is how I I went through this process, and I'm just going to summarize this for you. So what I did, for each of the 4 longitudinal states, I went through our equations and I just pulled out selectively the equations that we need. So like here is the equation for u dot. So I'm going to need that. That's our first one. I have the equation for w dot. That's the second one we need. And then, so those come from the translational dynamics. Then I go to the rotational dynamics. That's 3 equations. And I'm going to pluck out the q dot equation, because that's one of our longitudinal states. And then we just need one more, which was the theta. So that comes from the rotational kinematics. If you multiply this out, you get this. And we're plucking out this one. Theta dot is that. So we pulled out the 4 nonlinear equations. Shamik says, Professor, the homework for this week is due on Thursday, according to UB Learns. That's right. That's right. That's right. It's due tomorrow. Okay, so we grabbed these 4 nonlinear equations and we're going to linearize them. And we did some of this last time. Like we linearized this u equation. So I'm going to recycle. Okay, I was confused because it's usually due today. Yeah, you're right. I extended it by 1 day because I posted it a little later than I usually do. But yeah, it's due tomorrow. So we studied how you linearize a nonlinear state space equation, and essentially you have a perturbation in your variable about an equilibrium point, and that's going to be equal to, well, if I call this equation f1, I have to take the partial derivatives of that function with respect to all of the variables that show up in that equation. So we did some of this last time, but we took a bunch of partials and we ended up with this. What you see here with these going to 0, any term that has a star, you plug in the value from the reference flight conditions. So because this is a non-turning flight, we know that P, R, Q, these are all components of the angular velocity. Those are going to be equal to 0. So that's why you see P, Q, and R star equal to 0 here. And then V star was 0 because this was the side velocity. That's 0. Okay, so that's just some linearization stuff. Now, when you differentiate, hold on. You're going to see in each of these equations that we look at, these aerodynamic forces. Like the aerodynamic forces are capital X, capital Y, and capital Z. These ones get a little complicated because they depend on a lot of variables. And each of these might depend, how do I say it? It's kind of case by case what dependencies are important for each of these aerodynamic forces. So you'll see that today. But last time, I took the partial derivative of this aerodynamic force with respect to the elevator angle here and with respect to the throttle condition. But I forgot that this aerodynamic force along the bx body vector, it also depends on your speed along that direction. So basically, I forgot two terms. And it depends on this velocity. And you're certainly never going to have to memorize, like, okay, which partials are important to x or y, or they would all depend on velocity because they include dynamic pressure, right? Yeah, I think you're exactly right. But once we get to the aerodynamic moments, you're going to see that they depend on some extra terms. Like, well, we'll get to it, but I just want you to know, you don't need to, like, remember off the top of your head which partials are totally pertaining to each of these. Shamik says, another question about the homework. Whenever you give us Euler angles, the rotation matrix is always assumed to be 3, 2, 1, right? Most of the time. I would say unless it's specified otherwise, then assume that it's 3, 2, 1. Because that's the common configuration for aircraft dynamics. Okay, let's gather these terms. Yeah, you're welcome. Basically, the only terms that we're missing in this box are these two, so. Put that in here. Okay. So notice here that this linearized equation, you only see delta U, delta W, delta Q, delta theta. These are only the longitudinal states defined earlier. So it doesn't depend on like delta V, delta P. Those just don't show up here. So we'll keep going and you'll see this trend continue. So now we're moving on to that second equation. So we're going to have W dot, and we're going to linearize this. Let's do it a little bit at a time. But like if you take the partials with respect to Q and U, you're going to see, okay, I get these terms. This is just like product rule stuff. And then if I differentiate with respect to P and with respect to V, I'm going to get these terms. So basically, I'm just going through here term by term and differentiating with respect to the variables and just applying the product rule. The only tricky thing is, like I said, once you get to Z is a function of a lot of things, including the speed and whatever. So it turns out for this aerodynamic force, it's important. It depends on these two components of the speed. It depends on the elevator angle and also the throttle setting. So we're only taking those partials. Ooh, okay. I left the whole box blank here. So let's gather some terms. Usually we do the U term first. So this is the only one that depends on delta U. And then the second longitudinal state is W. And this is the only W or delta W term. We can't forget that 1 over m out in front that gets multiplied in. Our third longitudinal state is delta Q. Oh, wait. Some of these terms are going to go to 0. And let's do that right here. So like Q, this is an angular velocity. This is 0 because this is non-turning flight. V, little v is the side velocity. That's 0 because we're going straight. P is 0 because we're not turning. Because our wings are level, the bank angle is 0. So sine of 0 is 0. So this whole term goes to 0. For this, the bank angle is 0, but this is cosine of 0, so this term goes to 1. Okay, so that makes it a little simpler. Okay, so we got this term, we got this term. The next variable we like to do is delta Q. And that's just this one. And then delta theta is our last state. So I have minus G sine theta star delta theta. And then we can't forget about these two guys. These are our inputs from the elevator and the throttle. Let's get these in here. Okay. Once again, if you look at the variables that show up here, it's just our longitudinal states and longitudinal inputs. So we're just continuing that theme. Okay. So basically, the only point I wanted to make here is these linearized equations are only functions of the longitudinal states. Delta U, delta W, delta Q, delta theta, and longitudinal inputs. So that's the throttle and the elevator. And this is just happening through linearization. I'm not like somehow manipulating this to happen. Just when you go through the standard linearization process, it happens that about this reference flight condition that these equations are only a function of these variables. All right, so we've done 2 of the 4 equations and we found this to be the case. If you linearize for our third equation, which was Q dot, this is describing like the pitching dynamics, the nose going up and down caused by the pitching moment here. That's how you can think of this equation. When you linearize this, you're going to get a monster equation. So let me walk through some of this with you. So when I differentiate this, so what I did is these inertia terms are constant. So just think of that as a constant term. And what I did is I looked at this term first, which is a function of P and R. When I differentiate it with respect to P, then the only thing that's left is R, evaluated at the equilibrium condition. That's why it's R star. And then I have to multiply this by a perturbation in the variable that I took the partial derivative with respect to. So basically, from differentiating that term, I get this. From differentiating this one, P squared minus R squared, I'm going to get this line. Like P squared, if you differentiate that with respect to P, you get 2P. And then I multiply it by the perturbation in the variable I took the derivative with respect to. So this is just Taylor series stuff. But what really makes this monstrous... Oh, and by the way, because of our reference flight condition, R star is 0, P star is 0. So these two lines go to 0 anyways, it turns out, for this reference flight condition. Now, this M, this pitching moment, this is why this equation becomes monstrous, because there's a lot of variables that affect the pitching moment. So you see 6 of them right here that are important. So how do I know to differentiate with respect to these 6 variables? Well, I look at the Nelson textbook and they say, usually these are the important partial derivatives in practice. And that's what we do in flight dynamics. We go to some resource that says typically these are going to be the important partial derivatives. So we just look at those. So these are basically saying that the speed of the aircraft affects the pitching moment. So perturbations in that speed. Let's save this one for last, but a perturbation in the pitching rate will change the moment. And then obviously if you change your elevator angle, that'll affect the pitching moment. And if you add more thrust, that'll change the pitching moment. Now this one right here, this is saying that the pitching moment depends on the time derivative of this velocity component. So we actually have delta W dot show up in this equation. And that's why this becomes like a monster linearization, because what I need to do is take this huge expression for delta W dot and I have to substitute that whole thing in right here. You take that whole equation from the box, boom, substitute it in. I'm not going to make you write all of that. But this is what happens when you do it. I finished writing this up a couple hours ago. That's part of why the handout was so late. Look at that thing. It looks monstrous, but just, I think of these things like procedurally. Think about where it came from, and that's not too difficult to get that concept. And why is it so massive? Like, why does it have some of these z terms? Well, that came from the delta W dot equation that I substituted in here. Okay, the important thing to notice, though, is remember why we're doing this is we're looking at what states, what perturbations show up in these equations. And once again, we only see our 4 longitudinal states. We don't see any other stuff. And that just happened because of the reference flight condition that we linearize about. And then these are our 2 longitudinal inputs. And only these show up because, well, what are the other 2 inputs? The other 2 possible inputs are the rudder and the aileron deflection. And the rudder doesn't really affect the pitching moment. The rudder makes the aircraft yaw. It makes it turn left or turn right. And the ailerons make the aircraft roll. So those don't really affect pitching. So that's why those don't show up here. Those weren't important partial derivatives. Okay. So we have that monster equation. Ooh, this one's going to be a breath of fresh air. Because it turns out to be really simple. So this is our 4th and final state equation. And it's for theta dot. Okay, theta dot. So this was the equation. So delta theta dot. Let's linearize this together. And I'll do this really slow, step by step. First, we're going to differentiate this term. And you can see it's a function of phi, and it's also a function of q. So we're going to take the derivative of that product with respect to phi. And multiply that by delta phi. We're going to differentiate that. Oh, and we have to evaluate this at our reference flight condition. We're going to differentiate that with respect to q and multiply that by delta q. And then we'll look at this term. So I'll have minus the partial of that one with respect to phi times delta phi. And now I'll differentiate that with respect to r and multiply by delta r. Oh no. Okay. So, okay, we'll do this term by term. This will be minus sine phi, because I'm differentiating this cosine. And then I just have the q hanging out there. And I'm evaluating this at the reference flight condition. That's what the star means. And then I multiply that by delta phi. So that's the first one. And this one I'm differentiating with respect to q. So I just have cosine phi. And the derivative of q with respect to q is just 1. So I'm just multiplying that by 1. And then I have delta q. And then, here we go. So now we're differentiating this with respect to phi. And then we differentiate with respect to r. Oh wait, the r term will go away. And now here's the nice thing, because of our reference flight condition, a bunch of these terms go to 0. Like Q star is 0 because we're not turning. And double kill, this bank angle is 0 because it's wings level. Cosine phi is 1 because we're wings level. This term is 0 because R is 0. We're not turning. And this term is 0 because I'm taking sine of my bank angle, and my bank angle is 0. So it turns out, after having that monstrous equation for the last step, here we have delta theta dot is equal to delta Q, which is just adorable. One term in the equation. And we're just continuing this theme that this is not dependent on any states outside of those 4 longitudinal states. Okay, so in summary, all 4 of our longitudinal state equations only depend on each other. So we only depend on these 4 states. So we are totally justified in examining this reference flight condition, which is basically just straight flight at some constant altitude, no turning, with respect to only these 4 states. And once again, these 4, they're called the longitudinal perturbation dynamics. So if you ever hear longitudinal flight dynamics, they're talking about those 4 states. We're also going to go into the lateral flight dynamics, which has, for different reference flight conditions, you find different clusters of states that are interdependent on themselves, as you can imagine. Like if you're turning, a different set of states will be important, but you can still create a limited set of states. Okay, cool. Now we're going to organize these states in a linear state space form. But first, I'm going to introduce some standard notation for the partial derivatives. There's so many partial derivatives flying around that it's important to define some notation that'll help us out. So the notation that we have to help with this, these are called stability derivatives. And I'm going to show you a couple of them down here so you get an idea of what they are. We're only going to list a few, but there's something like 50 possible stability derivatives, and all they are, well, let's define this one. So this one is capital X sub u. And what this is, it's the partial derivative of x, that aerodynamic force, with respect to u, evaluated at whatever reference flight condition. But here's maybe the weird thing. You have to throw this 1 over m out in front. We've done other partial derivatives in this class where if I put the subscript, all it means is it's the partial derivative of that variable with respect to the subscript. But for the stability derivatives, it's different. So when you see this in the context of a stability derivative, it also means that there's a 1 over m out in front. And so it's the same thing with this stability derivative. It's just the partial with respect to w, but I need that 1 over m out in front. And with this z, which is another aerodynamic force, it's like this. Now, this stability derivative for the pitching moment is a little bit different. I don't divide by the mass. I divide by this moment of inertia term, Iyy. And the same with each of these. And I want to show you why. Like, this isn't totally arbitrary here. The goal of these is to simplify notation. So they try to pack some extra terms in here to save you writing time. Sorry. I'll let you write these really quick. But yeah, you'll see, because it includes this moment of inertia term, it allows your equation to look a lot simpler. Is that last partial supposed to be m with a delta E subscript? Yes. Oh, yeah, what am I doing here? Thank you very much. Yeah, m sub delta E. Thank you. Yeah. That doesn't really make sense otherwise. Okay. So these are stability derivatives, right? But I thought that was... Oh. Yeah, I don't know. My handwriting sometimes... Okay, so they're stability derivatives, but these are dimensional stability derivatives. Because, well, I guess it's a little obvious, but if you examine the units of these, you'll find them indeed to be dimensional. It's kind of like, well, why do you even have to say that? Like if I said, oh, this is mass, this is dimensional or something, you'd be like, yes, mass is kilograms or something. But the reason we distinguish between dimensional stability derivatives is because we're also going to have non-dimensional stability derivatives. So because we non-dimensionalize these, we have to make that distinction. So like if you look at this one, you'll see that it is dimensional because you have mass, and then you have this aerodynamic force, and you're dividing it by a velocity here. So this would be, if we did SI units, this would be newtons over kilograms times meters per second, for example. Okay, and we'll come back to the non-dimensional stability derivatives, but I just want to say one thing about them right now. You'll recognize them because we use the variable capital C. So the non-dimensional analog of xu is you have capital C and then a subscript xu. So we just add like more subscripts. So basically, you just have to take your dimensional stability derivative, xu, which is in newtons per kilogram times meter per second, and you have to multiply it by some extra terms to make it non-dimensional. So we'll come back to that, I guess, Monday. We'll come back to that on Monday. So we'll talk more about them soon. Okay, so we'll stick with the dimensional stability derivatives for now. So I want to show you how these simplify our writing. So this is the delta U dot equation that we had earlier. Let's write this with stability derivative notation. Okay, so right out of the gate, we have 1 over m times that. So this is going to be x u delta u. And then our second term is going to be x w delta w. This next term, well, it doesn't have any stability derivative stuff. It's just the same. Same with the next one. Cosine theta. Okay, this next stability derivative is a little weird because you see like these two terms together. Different textbooks do this in different ways, but I think the consensus is you have the thrust force here differentiated with respect to the throttle setting, and you also have the aerodynamic force along the nose with respect to the throttle setting. What they like to do is just call this x. So it's kind of like they combined them. And they just leave it like that. So they don't have like a capital T sub delta T plus a capital X sub delta T. It's kind of, when you see this X sub delta T, you just have to understand that it's the combination of these two. In my mind, that's one of the frustrating things about flight dynamics, because I feel like up until this point with our notation, you can be pretty clear of what something means. But once you get into these stability derivatives, I feel like it becomes a little more wishy-washy sometimes. So this is just one example of that. Okay, but then, okay, this last term is straightforward. X delta E. But you get the idea. The point of these stability derivatives is to make your life easier when you're writing stuff out. And we won't repeat this for all of them because I think you get the idea. Whenever you see a partial, you can pretty much substitute, just use subscript notation. So this is what happens when you do the delta W. And this delta Q equation, which took up a lot of real estate, now it looks a little more manageable. So this is where it made a better difference. Oh, and when we were talking about why is there a 1 over that inertia term, well, the purpose is so that no inertia terms show up in this equation anymore. They all got absorbed into these m terms. So it's just more saving you writing. So okay, and then here's this last adorable equation. It's their cute little friend. Okay, the last thing we're going to do today, we're going to put this into linear state space matrix form. And I already filled out 2 rows here. And maybe so we don't have to keep bouncing up, I'm going to bring this equation down here so we can just look at it. Let's just put it right here. Okay. So no problem. We've done stuff like this before. So we just have to say, okay, delta U dot is XU times delta U over here plus XW times delta W minus this nominal speed times delta Q minus G cosine theta times delta theta. And we still have these two input terms, but those go in the B matrix, which is just below here. So I'm going to have X sub delta T multiplied with my throttle input, and then X sub delta E multiplied with my elevator angle. So that's how this goes. Let's wipe this one out and then bring back our delta W equation and fill in that row. And then I'll just make a few comments about this. Because this, once you have this equation, this is where it starts to get pretty cool. So I'll give you a couple insights about this. Because this is where we start to be able to apply dynamic systems analysis to aircraft. So all of the tools that we learn in like our MAE 340 course, this is the connection between those tools and flight dynamics. Okay, so let's do this delta W dot equation. So I got ZU times delta U, ZW times delta W, U star times delta Q, and minus G sine theta star times delta theta. And then we just have these two input terms, Z sub delta T, Z sub delta E. So we have our 4x4 A matrix. We have our 4x2 B matrix. 4 states, 2 inputs. And so we just have like a standard state space model. And this will be fun because these dimensional derivatives here, these stability derivatives, you can find tables, well, in our textbook, but elsewhere, that say this is what this stability derivative is for a Boeing 747. Or this is what this derivative is for an F-16 or something. So once you have this equation, you can morph it into, for analyzing whatever aircraft you want. You just have to know what these parameters are. And they can be found. They can be found. Okay, so let's say you look up some of these parameters and you want to look at a 747 longitudinal dynamics. It's doing some straight flight in the sky. From dynamic systems, what we might be able to characterize is like, number one, the settling time. Like if there's a gust of wind upward that perturbs the dynamics of the Boeing, how quickly is it going to settle back down to its equilibrium flight condition? And you can calculate the natural frequency. Is it going to oscillate as it goes back? And we're going to start talking about this too, like what we call, there's what's called the phugoid mode and also the short period mode. But that's just fancy language referring to the natural frequencies of an aircraft in this longitudinal like configuration. You can, let's list a couple others. Damping ratio, something like overshoot. Like if you change the elevator angle on a Boeing 747, it'll cause the nose to pitch up or pitch down and reach a new equilibrium point. So you could say, oh, is it going to overshoot, or is it just going to like coast right into this new equilibrium point or whatever? So you can visualize like what's actually going to happen with the aircraft in these situations. So, and I think that's like the most important part. You can simulate how an aircraft responds to these inputs. And the reason I think that's the most important is, and we'll do some of this, this leads to the design of controllers that can stabilize an aircraft about a reference flight condition. Reference flight condition. Like for example, with this longitudinal mode, we're cruising at some altitude, with some speed, and I can design a little stabilizing controller that regulates the throttle and the elevator angle so that no matter what little perturbations, little turbulence in the air, the elevator will do some corrective action to just keep me on course. And I think that's the cool kind of end goal for this class. To be able to make controllers like that. And that's where I wanted to get today. I wanted to derive this state space model, and then this will allow us to pick up next week and get into these terms a little bit so that you can apply these equations to whatever aircraft you want to look at. Because we got to be able to put some numbers in here, but what are those numbers? What should they be? Is there going to be a homework next week? I think so. I think so, Dilly. I'm not 100% sure. Not 100% sure. You definitely want there to be homework next week, don't you? Because if I said no, there isn't, you would be like, wait. I need you to assign me something. That's what you were going to say, right? Oh, okay. I didn't think so. Let me see. I'm looking ahead a little bit. And since we have our exam this weekend, I don't know if we would get another homework. Yeah, I hear you. I think we might have a homework next week, but I'm looking at what it would be, and I think it would be an easier homework. I think our next one will be a little easier. Whenever we give it, just looking at what's going on here. It looks like a linearization kind of thing, but it's, yeah. Yeah. But Friday, we're going to do a test review. We won't meet on Twitch. We're going to meet on Zoom. Both flights dynamic sections will combine, and Dr. Ligor and I will do a review. We're gonna tag team it. We're gonna take all your questions. We'll try to give you an idea of the content of the exam, but that's the plan. So I'll shoot out an announcement about that. This is the end of, or we're approaching the end of week 7? Isn't it? And that means we are at the halfway point of the semester. Can you believe it? Holy cow, right? It goes by pretty fast. Because there's 15 weeks. You guys are getting the job done. It's not easy. Just waiting to hear when the 422 exam will be. I don't think it's been announced yet. Is 422 flight dynamics? I mean gas dynamics. Can you go over homework question 3 a little? I'm not sure how to connect the example in notes 11 and 12 to the problem to find actual solutions. Let me see here. Yeah, gas dynamics. Okay, gotcha. Assignment. Oh, he sent out an email? Okay, this is problem 3. So let's see. We have a reference flight condition. And this is kind of the flight condition we're looking at today. Steady, wings level, non-turning, no side slip. So, okay. So what's the question? Okay, we're finding the throttle setting needed to trim the aircraft, which basically just means to satisfy this condition at this speed. So what throttle setting do we need to achieve this flight condition? And then there's 3 cases. 3 cases where we're doing level flight, ascending, and descending. So you're asking, like, how do I connect this to the notes? I think it'll be notes 11. Without calculating z dot, can we know if the flight is ascending or descending? No, I think you need to know z dot. Wait, but I'll come back to that because you were talking about question 1. I'll come back to that to make sure I know what you're saying. All right, I'm gonna pull up notes 11 here. Wait, this one. I think this is similar to this example where, I mean, because like if you're ascending, descending, or whatever, it depends on this h dot parameter, right? So if h dot is positive, then you're ascending. If it's negative, you're descending, so on. So where does that come in? Okay, here. So like for one of the problems, what did it say? H dot is 500 feet per minute. Then, 500 feet per minute. Then if you're going here, H dot's gonna be 500 feet per minute. And it gives you like some conditions here. What else do we got? But basically, I think for that problem, the equations that come up in this example, 11.1, should apply. So if you're solving for the throttle setting, well, where does the throttle come in? Well, it could come in either of these. Like the thrust comes in here. And this is telling you how the thrust is related to the throttle. The thrust is T max times your throttle setting. And we tell you what T max is. It's a third of the weight of the aircraft. And the throttle setting should lie between 0 and 1. Okay. Oh, okay, and this is giving the lift and the drag. So I wouldn't use this equation. I mean, this equation, if you transform it into the wind frame, then it looks like this, and this is where lift and drag show up. And this thrust comes in here. So basically you can use the equations in here to figure out throttle and all those other things. But I think this example is the key for that problem. Okay, Rue, question 1C. Is the aircraft ascending or descending, and what is Z dot exactly? Hey, you're welcome, Arrow Guy. Yeah, I think you have to calculate Z dot to know, because you have to know if it's positive or negative. Yeah, you have to solve for Z dot. I do not think we have to use, can we just use Z dot is the rotation matrix UVW? Yes. Yeah, if you know the velocity components with respect to the body frame, you could use a rotation matrix to find the corresponding components with respect to the fixed frame, because that's where Z dot shows up, in the fixed frame. Oh, and I misspoke. Z dot, because it's pointing into the ground. You have to be careful when it's ascending or descending, right? Because if Z dot is negative, that means you're ascending. You're gaining altitude. And for 1D, I'm getting components of gravity in all three directions. Does it make sense? So what is D? It's in what direction, reference to the body axis, does the gravity vector act? That is it tilted towards the nose, left wing, etc.? Mathematically calculate the direction. Okay, so the gravity that acts in the Z direction with respect to the fixed frame, but what is the aircraft doing? Pitch angle, roll angle, yacht. Yeah, this makes sense that you would get components in all three directions, because it's kind of like it's nose up a little bit, it's rolled a little bit, it's yawed a little bit. Yeah, you're just transforming gravity from fixed to body frame. That makes perfect sense. Ranger says, in problem 2, how do we relate alpha dot to anything? Let's see. You're very welcome, Rue. At a particular moment during an acrobatic maneuver, a sensor measures the time rate of change of the angle of attack and the side slip angle. And you're solving for the angular velocity of the wind frame with respect to the body frame expressed in wind frame components. And so you're saying, how do we relate alpha dot to anything? Oh, because. So this problem, let me show you. It's like when we related Euler angles to the angular velocity in the body frame. Let me pull this up. Note section 9. Yeah, you need note section 9, but there's another set of notes. I would look at the Euler angle rate notes to get an idea of how you should structure the problem. Rotational rate, kinematics. I think what I'm looking for is in note set 5. Let's see. Yeah. You want to do something like this. Like you have the angular velocity with respect to the body frame. That's P, Q, and R. But I give you wind frame rates, like you have alpha dot and beta dot. That's kind of like this problem where you're given like psi dot, theta dot, phi dot. So if you structure the problem like this, that's what you're going for. Yeah, you're welcome. For question 3 again, there's 2 equations from translational dynamics that can let you calculate delta T, but they give you different answers. One is clearly wrong, so should we just go with the other one? Wait, that confuses me because I feel like they should both give you the same answer. Or did I mess up? It's possible. You get 0 from one of them? Are you talking about these? Like, are you talking about these 2 equations? Like the thrust is here and the thrust is here? Because we can plug in all the given values for the lift force and drag force equations. Yeah, because you got drag, you got lift. Last equation, weight equals lift for you. The angle of attack is 2.5 degrees. Interesting. Are you going on Discord? Oh yeah, guys, I gotta run. I have some road vehicle dynamics office hours on Discord right now. I have flight office hours tomorrow. We can talk about this. Thank you for hanging with me, guys. Thanks for learning flight dynamics with me. Wait, Rue, are you talking about road vehicle Discord? Because that's where I'm going right now. Flight dynamics Discord, 4:30 p.m. tomorrow. It's always from 4:30 to 5:30. Yeah, so since it's due at right. That's right. Yeah, shoot me an email. Good point. Our Discord is after the deadline. All right, my friends. See you soon.